Good morning, everyone. Consider this. At 2:47 a.m. on Black Friday 2019, Shopify's product recommendation cache expired. Within 3 seconds, 47,000 concurrent requests slammed their primary database, attempting to regenerate the exact same data. This led to a database CPU spike to 98%, response times ballooning from 20 to 4,500 milliseconds, and an 8-minute outage, costing an estimated $10 million in lost sales. This, ladies and gentlemen, is cache stampede, or the thundering herd problem, a critical, often underestimated, challenge in ultra-scalable system design. It's the digital equivalent of everyone in a stadium rushing through a single exit simultaneously. Today, we'll take a deep dive. We'll dissect its anatomy, explore robust solutions like request coalescing and probabilistic early expiration, discuss real-world implementation wisdom, and conclude with essential future trends. Our goal is to equip you with the knowledge to ensure your systems can withstand this digital onslaught. So what exactly is happening during a cache stampede? It occurs in a deceptively simple sequence. First, a popular item in your cache expires, leading to a cache miss. The very next request finds the cache empty and initiates a slow query to your primary database to regenerate that data. But here's the critical catch. Before that initial, slow database query can complete, hundreds or even thousands of other concurrent requests arrive. Each of these requests also finds the cache empty, and crucially, each one fires off its own identical database query. This creates a massive surge of redundant work. Your database, designed for efficient single query operations, quickly drowns under this sudden, overwhelming weight of identical requests. This cascade failure can bring an entire system to its knees. Twitter, Reddit, and Instagram have all publicly documented such incidents. The pattern is universal. High traffic, combined with cache expiration and a slow data source, is a recipe for catastrophic cascade failure. The first line of defense, and often the simplest and most effective for around 80% of cases, is request coalescing. This strategy ensures that only one request is allowed to regenerate expired data, while all other concurrent requests patiently wait for that single regeneration to complete. When the first request detects a cache miss, it immediately attempts to acquire an exclusive lock for that specific cache key. Subsequent requests for the same data will find this lock in place. Instead of querying the database themselves, they enter a waiting state, typically polling at intervals or using a pub/sub mechanism until the lock is released. Once the lock holder successfully regenerates the data and populates the cache, it releases the lock. All waiting requests then read from the freshly populated cache, getting a fast cache hit. For implementation, a common and robust pattern involves using Redis set and X, set if not exists, with a short time to live, or TTL, as your distributed lock. Critically, set the lock timeout slightly longer than your worst-case database query time to prevent premature lock releases or deadlocks if the regenerator crashes. This approach centralizes the expensive data regeneration work, drastically reducing database load. While request coalescing handles immediate stampedes, probabilistic early expiration offers a more proactive approach, preventing the cache from ever truly going empty. Instead of waiting for an item to fully expire, this strategy randomly refreshes items before they expire. The probability of triggering an early refresh steadily increases as the item's expiration time approaches. Imagine an item expiring in 60 seconds with 10,000 requests per second. Statistically, one request will trigger an early refresh around the 50-second mark. This clever technique, often implemented using the xfetch algorithm, effectively spreads cache regeneration over time, smoothing out potential spikes. The math behind it is elegant. Should refresh equals time to expiry over original TTL is less than a random 0 to 1 times beta. When the cache is fresh, the refresh probability is near 0. As it ages, the probability increases significantly. A beta value of 1.5 is often a sweet spot in production, offering a balanced approach between conservative and aggressive early refreshing. This method particularly shines when you can't predict traffic patterns, as it naturally load balances the regeneration effort across time. Now, how do we apply this wisdom in the real world? Your cache strategy isn't a one-size-fits-all. It should answer 3 critical questions. First, can your database handle the load if the cache completely fails? If no, you absolutely need request coalescing. Second, can you tolerate occasional slow requests? If not, probabilistic or background refresh are essential. Third, do you have traffic patterns with predictable spikes? If yes, pre-warming your cache is key.
The provided content includes an automated comparison, vividly demonstrating the impact a naive implementation shows, hundreds of database queries, while request coalescing reduces this to 3 to 5, and probabilistic expiration to 8 to 12, a drastic reduction in both cases. Implementation wisdom also involves careful tuning. Adjust parameters like cache TTL for write-heavy versus read-heavy workloads, and calibrate lock timeouts and polling intervals based on the criticality of your paths. For instance, a generous lock timeout for critical paths, or a shorter one for non-critical ones. Remember, the ultimate lesson is cache stampede is a coordination problem, not just a caching problem. It's about smart resource management. Beyond the primary solutions, there are advanced defenses and essential practices to consider for future-proofing your systems. First, background refresh decouples cache reads from writes entirely. A dedicated process proactively monitors expiration and refreshes data before it expires, ensuring your application always reads from a warm cache. This is essential for ultra-critical paths as used by companies like Netflix. Cache warming pre-populates your cache before expected traffic spikes, and multi-tier caching adds further layers of resilience. Finally, robust monitoring and instrumentation are non-negotiable. Track metrics like cache hits, misses, and database queries. Set up timely alerts for Stampede indicators, such as database query rate spikes or cache hit rate drops, and implement a critical circuit breaker for total cache failure,